Hello AP Chemistry and welcome to calorimetry, okay? Calorimetry is the one way that we can experimentally determine delta H. Calorimetry is the one way that we can experimentally determine delta H, also known as enthalpy, also known as heat of a reaction, okay? Or a process. It doesn't have to be an actual chemical reaction, but calorimetry is how we determine the heat of a process, okay? Here we have a standard very basic calorimetry setup, okay? Turns out that styrofoam cups are great for this, which is why that's what we use most of the time. And they happen to be decidedly affordable, right? Which makes them great for high school chemistry use. And actually your introductory college chemistry courses also for the same reason. So note that important things to note here, right? Thermometer. Calorimetry, right, or delta H is what? Heat, right? Where heat is the exchange of energy resulting in a temperature change, right? Which means that obviously we're going to have a thermometer, because a thermometer is what's going to allow us to know, right, how much, well, that's going to help us to quantify the amount of heat exchanged, okay? Here we have a stirrer, simply because we want to keep our things mixing in here, right? Because, for example, going back to that thing we talked about earlier, if we were to dump calcium chloride in here, right, we need to make sure that that calcium chloride is actually being distributed throughout our entire sample. So stirrers, or a stirring method, is always employed, right? We have a stopper. Why do we have a stopper? Right, because we only want to measure the amount of heat being exchanged in here. If we don't have a lid, right, then heat is not only being exchanged here, but also here with the outside environment, right? And we want to try to limit, right, our experiment, right, to just a system and preferably one surrounding as opposed to multiple different surroundings where we have to track our energy, okay? Here we have two nested styrofoam cups. Why do we use two? Right, simply for an extra layer of insulation, right? And here we have our reaction mixture. Now, here, right, when we're doing this, right, really, really important, the water is almost always going to be our surroundings. Okay, because let's say that we are, for example, we could be dissolving CaCl2, right? Or we could be doing some kind of neutralization reaction. Or we could be doing a metal plus an acid reaction, right? We could be doing any kind of these reactions in here, right? But the point is that there's always going to be a water component, right? Here, it's going to literally be the water sitting in there, right? If we do a neutralization, right, we are going to have our acid, which is going to be aqueous, plus a base, which often is aqueous, right? And aqueous means what? Dissolved in water, right? Which means that water is always in the background of what's happening, right? It doesn't participate, but it's always in the background, right? Likewise, if we have a metal, right, my metal is going to be a solid, but my acid is going to be aqueous, right? Which means, again, water in the background, okay? So water is going to play our surroundings, and the actual species in the water are going to be our system, okay? Really, really important. Because we can't physically measure, right, what's happening to the calcium and chloride ions, but we can measure what happens to the water, right? Again, we can't measure the interaction of these ions with one another, but we can measure what they do to the water, right? Likewise here, we can't measure this, we can't measure what happens between these particles, but we can measure their effect on water, right? And now that means if my water absorbs heat, if my water goes up in temperature, if we increase the temperature of my water, right, that means the reaction released energy. Yes? And if we decrease the temperature of my water, that means my reaction absorbed energy. That says absorbed. Okay? Water is always going to be our background. If we increase the temperature of my water, it's because, again, going back to the first law, right, has to come from somewhere, right? It's because the reaction or the process released energy. If the temperature of my water goes down, right, bearing in mind that at room temperature even, right, water is approximately 25 degrees Celsius, which means that it has all that energy stored, right, as part of the kinetic energy associated with being 25 degrees Celsius, which means that if the reaction needs energy, it will take it from the water, right? And the water will cool down as a result. Okay, let's do a problem. Really, really important that we track our sign, just like we talked about in that other problem. So let's go ahead and read it, right? We have 50 mils of 0.1 molar blah and 50 mils of 0.1 molar HCl are mixed in a constant pressure calorimeter. Constant pressure calorimeter. Going back to this one, right? We do have a cork stopper on here, right? But right, it is still basically open to the atmosphere, right? Because we're not completely sealing it in like a bomb calorimeter, for example. Okay. Okay. So it says that I should have spaced this differently, but the temperature of the mixture increases from 22 to 23.11. Okay. The temperature increase is caused by the following reaction. The question even worded so easily for you. Calculate delta H for this reaction in AgNO3, because we have to have a point of view, right? Assuming that the combined solution has a mass of 100 grams. Why are we saying that the solution probably has a mass of 100 grams? Right, because these are relatively dilute, okay? So if we're talking about decimal values of molarity, that's relatively dilute. If we're talking about like greater than 1, like 2, 3, 4, 5, 6, 7, etc., that's considered a relatively concentrated solution. Concentrated meaning lots of moles per liter. If there are lots of moles, that means there's an increased number of particles. In that case, right, it's probably not going to be the density of water, okay? Here, though, since they are dilute solutions, we can kind of assume that this is approximately 50 grams, this is approximately 50 grams, which gives us approximately 100 grams. And a specific heat of this, which we recognize as being the specific heat of, ding, 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 water, right? Because, again, as long as my solutions are relatively dilute, right, we can assume that the constants that apply to water apply mostly to this mixture also, right? Or the chemical reaction that's going to occur here. All right. So obviously, I think we understand that we're going to have to do a Q equals MC delta T. Okay, so let's go ahead and define all of our parts. And this is just how I prefer to do it. We're going to define all of our parts, right? So Q equals MC delta T. We have to find Q. Now, our goal is to find the Q of AgNO3. Okay, which is going to be equal to the opposite of Q water. Yes? The Q AgNO3 is opposite of Q water. Yes? All right, let's put that tidbit aside. Now let's go ahead and calculate the Q of my water. Q of my water is equal to mass times C times a delta T. So the mixture increases from 22 to that, right? So 23.11 minus 22.30 degrees Celsius, okay? Which means that the Q of my water is equal to, so we have 100 times 4.18 times, what am I looking for? 23.11 minus 22.3. So we get 338.58 joules, okay? And note that here, right, the answer is positive because the temperature of the water increased, right? Now, going back over here, they are going to be opposite, right? Which means that if this is the energy absorbed by water, because there's a positive sign here, right? This is the energy absorbed by water, all right? Therefore, Q of my reaction is equal to negative 338.585 joules. Yes? Then this is the E released by the reaction. Yes? Okay, we're not done because this is the total amount of energy released by the reaction. And our question is asking us to tie that back to AgNO3. So in order to do that, we're just going to have to go back to our problem. And we know that we started with this much AgNO3 and this much HCl. Here, again, we know the amounts of both reactants, so it's kind of like a limiting reactant problem, where we have to look at this and we say, okay, well, if we have 50 mils of this, how many moles do we have? This is 0.05 liters times 0.1 moles per liter, which means we have 0.005 moles of this and 0.005 moles of this, okay? Which means that there's no limiting, right? They are stoichiometrically equivalent, which means that And that's important because if this were the limiting reactant, right, that would limit how much of this we would have reacted. Yes? If this were limiting, it would have limited how much of this would have reacted, and we wouldn't have used all 0.005 moles. Okay? So now, in order to find the Q as it relates to AgNO3, we're going to go ahead and take our negative 338.585. I think it's just supposed to be 58 joules, yes. And we're going to divide that by 0.005 moles of AgNO3, okay? And this is also equal to the delta H, right, of this process as it's tied to AgNO3. So if we go back and we take this number and we divide this by 0.005, we end up with that number, which then, remember, our units are important, right? So we know it's 677. Then we have to figure out our number of sig figs, right? Which if we go back through our math, this is going to limit our sig figs here because when we do this subtraction step, right? So we're going to do joules, right? Which then if we round it appropriately is going to be this many kilojoules. Yes? Yes. And that's because we had to tie it back to AgNO3. Yes? Fantastic. All right, let's do one more. This one, so it says we have X grams of lactic acid burned in a calorimeter. So burned in a calorimeter means we're talking about bomb calorimetry, okay? Whose heat capacity, right? And when we go back to heat capacity, right, that's the amount of energy absorbed to change the temperature, right? So this is the heat capacity, and we see that this is an energy per temperature. The degree sign got left out. Energy per temperature. The temperature increased from blah to blah. Calculate the heat of combustion per gram per mole. Burned means combustion, yes. Okay. So if we know that this calorimeter requires this much energy to change 1 degree Celsius, oh, look, we also happen to know that over here, 24.95, 23.10, right? We know that we had a temperature change of 1.85 degrees. Uh-oh. What can we calculate here? Right. So if we do this, so 4.812 times 1.85 is going to give us 8.9 kilojoules, yes? So that's the total amount of heat absorbed by the calorimeter, yes? Heat absorbed by the calorimeter. Which means that that heat, ding, 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 was released by the combustion process, right? So if we want to make it per gram, we're just going to take my 8.9 kilojoules and tie it to my grams. So 0.5865 grams of my lactic acid. And then obviously you're not going to leave it like that. You're going to go ahead and take that and divide it by 0.5865, right? Which is going to give us our 15.2 kilojoules, right? Per gram of my lactic acid. If we want to turn it into per mole, right, we would have our 8.9 kilojoules. Well, actually, no. Here, let's start with this one. So if we have 8.9, why do I keep writing that? You can go back to the 8.9. I was just trying to keep moving here. If I have 15.2 kilojoules per gram, and I know that, right? And this is per gram of lactic acid, which is HC3H5O3, right? Unit analysis says I can take the molar mass of HC3H5O3 over 1 mole of HC3H5O3. I can calculate its molar mass, put it up here, right? So just really quickly, right? We have 1.01 plus 3 carbons, which is 36.03, plus 5 of those, plus 3 oxygens, gives us 90.09, right? And then now we cancel those parts, right? And we've converted this into kilojoules per mole, yeah? All right. Very good. This is calorimetry, which again, the only experimental method to determine the heat of a reaction. or the heat of a process. Okay, the next few sections we're going to talk about how we can calculate the heat of a reaction or of a process using calculations and data that has already been pre-collected as opposed to experimental numbers. Thanks for listening. Be good, and I'll see you soon. Bye.